Hey Team Bio, welcome to your screencast on atomic structure. So we've taken a little hiatus from screencasts in order to read the climate action plan, but now we're back. Our next unit is we're going to be talking about organic molecules, the molecules that make up living things, as well as organelles and cell structure and function. So really, in order to understand all these things, we have to understand how atoms are put together. So I fully expect this screencast to be a complete review of things that you already learned in methods and in middle school. You already know that the atom is the smallest unit of matter. And there are a bunch of different models of atoms. Two that you likely learned last year. So these are both atomic models of helium. Helium is an element. This is called the planetary model. It might also be called the Bohr model, the person who proposed it. And then this is the quantum model. There are two different images showing us essentially a very similar thing. The planetary model is showing us electrons that are orbiting in kind of a specific orbital, a specific region, whereas the quantum model is saying that these two electrons are in a cloud of probability. This is an electron cloud. And they could be anywhere, but they're most likely to be in the darkest shaded regions of the model. Okay, so two different models, both of helium, each showing us similar information. The only difference being here we have an electron cloud and here we have discrete electrons. Okay, so atoms are made up of subatomic particles. We have protons, neutrons, and electrons. Oops. Protons and neutrons are found in the nucleus. And this area right here is the nucleus in both of these models. And then electrons orbit the nucleus in orbitals, regions where they are likely to be found. Okay, so protons have a positive charge, as you can see right here. They are positively charged, they're found in the nucleus, and the number of protons in the nucleus determines the element. Because this element has two protons, we know for a fact that it must be helium. Okay, let's go over to here. This is a abbreviation of helium that we'd see in the periodic table. It's made up of a couple different parts. Here we have the symbol for helium. Here in the upper left-hand corner is the atomic number. The atomic number is the number of protons in the element. Oops. My eraser's too big. In the element. here we see the name. And here we see the atomic mass. The atomic mass is equal to the number of protons plus the number of neutrons. Okay, which brings us back to our diagram over here. We have 2 protons in the nucleus of this atom, so we know it must be helium, and we have an atomic mass of 4, so we know there must be 2 protons and 2 neutrons. Neutrons are neutral. They do not have a charge, but they help stabilize the nucleus. As you can imagine, when we get a bunch of charges and positive charges, and we put them close together, they want to repel each other, push away from one another. But there's a force that is holding the atoms together, and the neutrons help supply some of that force. So the number of neutrons in the nucleus helps determine the mass, but so like adding a neutron or taking away a neutron would change the mass of the nucleus and therefore the atomic mass of the element. But it also would change the stability of the element. If you add too many neutrons or you take away too many neutrons, the nucleus becomes unstable. So it determines the mass / the stability of the nucleus. An isotope of an element is the same number of protons, but a different number of neutrons. So it's the same element, but with a different number of neutrons. So there are a couple different isotopes of helium. The 2 stable versions of helium are this, which is helium-4, which has 4 particles in the nucleus, but helium-3 is also stable. It has 2 protons and 1 neutron. If you have an unstable number ratio of protons to neutrons, you create what's called a radioactive isotope. This is where the ratio of protons to neutrons is unstable. And then the atom is going to decay. It's going to, we're not really going to get into radioactive decay, but it'll change if the ratio of protons to neutrons is not in a stable ratio. Okay, so that's protons and neutrons. Protons determine the element, neutrons determine the isotope, and which is like both the mass. If we change the neutrons, we're going to change the mass, and we're also going to change the stability of the nucleus. Okay, the electrons determine the charge. Okay, so if the number of electrons in the atom is equal to the number of protons, this leads to a neutral atom. kind of makes sense. This has one negative charge, this has one positive charge, so if the numbers are balanced, then the atom is neutral. If you remove an electron, I just say remove electron, you create a positive ion. This means an ion is a charged atom, and if you take away one negative charge, you're left with an overall positive charge on the atom. So you create a positive ion. If you add an electron, you create a negative ion. Electrons have a negative charge, so if you add an additional electron, now the atom becomes negatively charged. It is a negative ion. Okay, so this is basic atomic structure. Here is the overall periodic table. These are all the different elements. There are two, they're organized into groups and periods. Or I should say group and period. I don't think it's plural. Group and period. And they're organized, if you move from left to right across the group, it increases a proton to create a different element. And if you move down a period, you move into new orbitals. More about that tomorrow. So properties of elements, it depends on their chemical structures and how much they want to bond with other elements or not, as well as how willing they are to give up or receive electrons. So that gives all the elements that we see the different behaviors that we observe in the world. And more on chemical bonding next screencast. Okay, that's all.